Okay, let's dive right in. If you've ever built a deep learning model, you know the feeling. You've hit that wall, that point where your model just refuses to get any better. It's this super frustrating experience, right? Well, today we're going to pull back the curtain on a really powerful debugging technique called gradient checking. Think of it as the secret tool that makes sure the very engine of your model is running the way it's supposed to. I mean, this is the question that keeps machine learning engineers up at night. You've dotted all your I's, crossed all your T's, the code looks perfect, your data's clean, the architecture seems solid, but the loss just isn't going down. The model is just sitting there, dumb and stubborn. So what is actually going on? Now, here's the really tricky part. Unlike a normal coding bug, the kind that crashes your program with a big, obvious error message, a bug in your learning algorithm is, well, it's silent. It doesn't stop the code from running at all. It just stops it from learning. So the model trains and trains, but it learns absolutely nothing. And you're just left scratching your head. So let's get under the hood and figure out what's going wrong. When a good model starts to go bad, it almost always comes down to a problem in one single critical process. And this is it, backpropagation. This is the mathematical heart of your neural network. It is a truly brilliant and efficient way to figure out how every single weight and bias in your model affects the final error. But, and this is a big but, it is incredibly delicate and notoriously complex to implement from scratch. And because it's so complex, it's just so easy to get wrong. Just look at this list. We're not talking about huge, obvious mistakes. It's usually something tiny. A misplaced index, forgetting to add in a regularization term, or getting a derivative formula just slightly off. These are the kinds of subtle bugs that can completely corrupt the entire learning process. This quote just nails it. It perfectly illustrates the stakes here. See, gradients are the signals, the directions that guide your model toward a solution. If those directions are wrong, your model is essentially getting bad GPS. It's going to get completely lost, and the whole learning process just falls apart. So, to really get why this is so critical, we need a solid intuition for what these gradients actually are. Let's build a simple mental model for this engine of learning. This is honestly the perfect analogy. So picture it. The mountain is your loss function. It's this big, complex landscape of errors. Your goal is to get to the lowest possible point, the valley floor, where the error is at its minimum. But you're blindfolded. The only information you have is the slope of the ground right under your feet. That slope, that is the gradient. It tells you which direction is the steepest way down. And here's the punchline. The entire training process, which we call gradient descent, is really just about taking a small step in the direction the gradient tells you to go. That's it. Step by step, you follow the slope downhill. But if your gradient is wrong, you might start walking sideways, or even worse, you might start walking uphill, getting further and further away from the solution. Okay, so we've established our gradients have to be perfect, but we also know that backpropagation is super easy to mess up. So how do we solve this puzzle? Well, we need a check. We need a mathematical safeguard to verify our own work. And this is the core idea of gradient checking. We actually have two different ways to calculate the gradient. The first way, the analytical gradient, comes from backpropagation. It's fast, it's elegant, it's based on pure calculus, but it's where we might have bugs. The second way is the numerical gradient. It's a slow, kind of brute force, but very reliable approximation. So you can think of it as the ground truth. The whole game is to use the slow one to double check if our fast one is actually correct. So how does this slow, reliable ground truth method even work? It's actually built on a wonderfully simple and intuitive idea that we can just call the nudge test. Yeah, that's right. Instead of using complex calculus, we just experiment. We literally pick one single parameter out of the millions in our network, and we nudge its value up by a tiny, tiny amount. Then we run all our data through the entire network again just to see how that one little nudge affected the final loss. That real-world change gives us a surprisingly good estimate of the gradient for that one parameter. So, how do we make this little test even more accurate? Well, instead of just nudging the parameter up, we do a two-sided test. It's super straightforward. First, you see here, we pick a parameter and add a tiny amount. We'll call it epsilon. And then we compute the loss. Then we go back and subtract that same epsilon and compute the loss again. The formula then just gives us the change in loss over the total change in the parameter. This gives us a much more precise estimate of the true slope. It's called the central difference approximation. And what about this tiny nudge, this epsilon? Well, this value you see here, 10 to the power of -7, is a pretty common choice. You can think of it as a Goldilocks value. See, if it were too big, our approximation of the slope wouldn't be very accurate. But if it were too small, we'd start running into weird floating point precision issues with the computer's math. So this value, it hits the sweet spot. Okay, so that's the theory. But how does this actually translate into something we can use in the real world? Well, there are some very, very important rules to follow when you're putting gradient checking into practice. The first rule, and honestly the most important one, gradient checking is incredibly slow. I mean, just look at this chart. Remember, for every single parameter in your network, you have to do 2 full forward passes. If you have a model with millions of parameters, well, this is just computationally brutal. And that is why you never, ever use gradient checking during actual training. It's a debugging tool and only a debugging tool. So here is your essential debugging checklist. First, and I'm going to say it again, use it for debugging only and then turn it off for actual training. You also have to disable anything that adds randomness, like dropout. Otherwise, you won't get a consistent result. And here's a really critical point. Don't forget to include your regularization term in the calculation. That is one of the most common places for bugs to hide. So you might be wondering, does this even matter anymore? If you're using standard, off-the-shelf layers in a major framework like PyTorch or TensorFlow, their gradient calculations are already heavily tested and, they're correct. So you'll rarely need to do this. But the moment you decide to write a custom layer or a new activation function, or you're just debugging some really strange model behavior, this tool becomes absolutely essential. All right, let's wrap this up by zooming out a bit. Why is understanding a debugging tool from, the early days of deep learning still so important today? It's because it all comes back to our analogy. You're on that mountain, you're blindfolded. The gradient is your only guide. Gradient checking is that one moment where you can just take a pause and verify that your slope sensor, your backpropagation code, is actually working. You're confirming that your guide isn't lying to you before you continue on the journey. And ultimately, this isn't just about finding a bug. It's really about a mindset. It represents a commitment to careful engineering, to ensuring the mathematical foundations of your model are solid before you go and invest hundreds of hours in training it. It's a sign of real discipline. And I'll just leave you with this thought. The entire spectacular success of deep learning, all of it, rests on this simple, humble gradient. So knowing that, what does it mean for us as the builders and the engineers to approach our work with the kind of discipline and rigor that such a powerful yet delicate foundation truly deserves?